Can you please let me know which week you are following right now? What is the topic you are going through right now, according to ma'am's class? Anyone can type. I mean, which week you are following course. Hi, Venkatesh.
Good evening, sir.
So, which week you are following? What is the topic you are going through from ma'am's course?
Still, I am in week 6, sir.
Week six. Week six content. What? Kinetic isotope effect.
Yes, professor. Yes,
Okay.
sir. Kinetic isotope effect and
Okay.
excuse me,
Okay. Thank you.
heavy atom isotope effects, then
Okay.
equilibrium isotope effect,
Okay. Thank you.
isotopic labeling, and trapping of intermediate. These things.
Got it. Okay. Sure. Thank you.
Thank you, sir. Thank you, sir.
If my screen is visible.
Yes, sir. Yes, sir.
Okay. Thank you. Okay. It's 7:05 and let's start. I think everything is okay. Fine. Now, what we have is simple slides and few questions which are very easy to understand. I don't think there is so much complicacy except some part. Others are very easy to follow. Let's go ahead. Welcome again. My name is Manajit and I will be talking the kinetic isotope effect. Basically, few questions from Carrie Sandberg and few from Clayton. Okay, these two are the references. You can always look those books. It's very well written and you can go through them. So first I will try to give a very broad idea, not going into very depth into the physical chemistry part. Within a single plot, how can we understand the kinetic isotope effect? So what it is actually. So I have a one picture here. This picture itself describes what is kinetic isotope effect. Let me elaborate here. So in the y-axis, you have energy. So, so this is the potential energy curve for a bond vibration. Okay. Now, so kinetic isotope effect. So there will be something related to isotope. Okay. So what it shows here, I have a red colored potential energy curve. Okay. Uh, Now in the below, my cursor is here. You can see. So there is a orange or yellow color bar which represent the 0 point energy. This is the CH bond, and the yellow color, see this double headed arrow is shown. So this correspond to the 0 point energy for a CH bond. Okay. So from the deep down here, horizontal red dotted line to the CH bond. So this is the vibrational level, the 0 point energy for CH. Okay, this energy. So it has this energy CH. So if I read it like any CH bond has characteristic vibration. So this CH bond has a characteristic vibration, which imparts some energy to the molecule in its normal state. So it will impart some energy. Let me. So this is the situation. Now, if you what we are doing here, let's say we replace that CH bond. We are not discussing any molecule. It can be, it doesn't matter which molecule we are talking. In a molecule, whatever of your interest, imagine that you are replacing one CH bond with a deuterium, that is another isotope of hydrogen. So what will be the effect? So the effect is their change in 0 point energy. Hmm? So the CH bond has a 0 point energy here, and then CD bond, it has a higher mass. Deuterium has a higher mass compared to hydrogen, and we can see that it has a lower 0 point energy compared to CH bond. So in the right side that we saw, lowest allowed vibrational energy levels. So this is the lowest vibrational energy level. So this is a CH, the vibrational energy level is a little high, so higher energy compared to CD. And you may ask why this CD is lower, why than CH. Basically, the equations of how the reduced mass depends the energy of vibration that comes from here. That's why we see the lowering energy. Now, so this is in a ground state or normal in a stable state. Now, why we are following this? Why CH and why CD bond? The problem in our hand is that, let's say we have a reaction where we want to understand whether this CH bond or CD bond is undergoing cleavage in the rate determining step. So what will be the rate if we replace that CH bond with a CD bond? So that's the goal. What is the effect on rate if we replace a CH bond with its isotope? If we replace with CD bond. So we have a background now. Now, what happens when it goes through a transition state, right? Any reaction. So there will be one path for CH, another path will be for CD. Now, we are assuming that in the transition state, the the reactivity is doesn't alter in a great extent. I mean, the in the transition state, this energy difference between CH and CD is very small, or it doesn't matter at initially. We are assuming that. So what happens? That's why here they have shown a red color horizontal line at the middle. You see. So which we are assuming that there is not so much difference. So the rate is transition state is not that much affected. The energy difference. So what it turns that from the CH bond to the activation energy here, which is shown in delta GH. So energy required to break CH bond. So this is the energy which we require to break the CH bond, which is less compared to the CD bond. So here we see that CD bond has a higher energy requirement to break. Okay. So this in turn shows that we will need the KH, we will get what activation energy of CH bond is less compared to activation energy for the CD bond. So what is the consequence? The rate of reaction in which there is a break of CH will be high. The rate of the reaction in which there is a breakage of CH bond will be high because it has a lower activation energy. Whereas in the corresponding rate for the CD bond breakage will be, it will rate will be less. Okay. So what we can write actually is that basically we are comparing two rate constant. So we have a rate constant with a hydrogen atom and we have another rate constant with a deuterium atom. Now since the rate is fast because of lower activation energy, so rate is high here, I will say. This is very basic introduction, you can follow it anywhere. So activation energy is low and KT is lower rate, activation energy is high. So this is the simple equation. So the effect is the ratio between Kh by Kt is greater than 1. Okay. So this is what known as typically kinetic isotope effect. So if I summarize this, the replacement of a bond with Kh hydrogen with its isotope deuterium results in lowering of the rate. Thus, the Kh by Kt is greater than 1. This is typically known as kinetic isotope effect or primary kinetic isotope effect in general. So, uh, remember we are talking about that in the rate determining state there is a cleavage of the CH or CD bonds. Then only we are thinking it like in this. Okay. Now, what will be the value typically of these things like ratio? So it says that if you actually this can be proven, there is a division. So the highest maximum value of Kh by Kt is around 7. So it is typically written that Kh by Kt maximum value is 7. Now you can see some examples also where Kh by Kt more than 7. So there are high values also there, but those are not general case. So there will be some tunneling and other things which is not of our discussion topic. So with this introduction, I would like to show some questions and then we'll go there. What else I have to discuss is that. So now imagine if we have a kinetic isotope effect of very high value, let's say 3, 4, 5, 6. We can conclude that this involves the breakage of CH at the rate determining state. Okay. Now let's go ahead and check some equation. So this equation, it's written like this. For example, the rate of these two elimination can be compared. So again, as I said, we will be comparing CH bond with the CD bond. So in the left we have CH and the right we have CD. And KH by KT turns out to be 7.1 at 25 degrees Celsius. So what is the conclusion is here that the rate KH is high compared to KD. So KH will abstract proton here. So and then this CH bond will break and it will expel the bromine. Okay. So the corresponding deuterated system will follow the same path, just that the rate will be lower. That's why we get a Kh by Kt value of 7.1. So this is a typical example of primary kinetic isotope effect. Remember, primary kinetic isotope effect involves the bond which is breaking, like CH bonds which we are talking in here. Okay. And then let's take another example. These examples I already discussed in some other earlier classes. So let's say we don't know the reaction mechanism of aromatic electrophilic substitution. One mechanism can one propose that the CH bond is breaking directly. There is a hydrogen here. Imagine there is a hydrogen here. I talked earlier also. So whether it is simultaneously hydrogen breaking and NO2 addition or it's a two-step. So one of our friends said we can get the intermediate and then prove then also which is correct. We can trap the intermediate also. There is this procedure which is also elegant. There we can check the primary kinetic isotope effect. So basically our task is, okay, replace one hydrogen. All hydrogens are equivalent here in benzene. So replace one hydrogen with deuterium atom and check the corresponding rate. So if you do the experiment and hydrogen replace and deuterium, then do the nitration like NO2 plus. So you see, you don't know the mechanism, right? Initially you don't have any idea. You do two experiment, one with hydrogen, one with deuterium. So you have two data. One with kh value will be something, let's say x, and then the kd value will be, let's say, y. So basically these two appears as same, kh by kd equal to 1. So the rate determining step, so what it means actually, it doesn't matter whether it is hydrogen or deuterium, whether it doesn't matter, the rate remains same in general terms. So rate remains same. So that's why we don't see any observable very high number here. Kh by kd is 1. So whether it is hydrogen or whether it is deuterium, the rate remains more or less same. So we can conclude that the pi electron first attacks NO2, which is the rate determining step, which doesn't involve any hydrogen or deuterium, nothing to do with that. Whereas in the second step, this CH or CD bond will break, and which is very fast. This is very fast, and we get a nitrated benzene. Well, there can be some question like in the second step there is some involvement of the CH and CD bond. Why it is not affecting the rate value? The main part is this rate determining step. There may be some effect, but majority is part is contributing from this factor. If it is done, then the rest of the thing doesn't matter actually. So overall, if it doesn't matter whether it is hydrogen or deuterium, we get a kh by kT value of 1. Now I have a question for you, and I will give some time to think about it. What will be the this aromatic electrophilic substitution reaction kh by kT value? Do you expect this value to be high, or it should be similar to the case I showed to you? So I will give 1 minute, and please come up with an answer in the chat box, or you can say it too. So let me show the reaction otherwise. Please note down the reaction and let me know what you think this kh by kT value will be. So what is the time? It's 7:19. I will give 1 minute. So 7:20 I will start again. So some message. Is fast, kh by kd is greater than 7. Anyone else? Jagabandhu or Ankita, Pallavi, Christina? Others also can answer, please. It would be nice to have your response. Just guess it. It's not a big deal. We may be wrong, we may be right, doesn't matter. Okay, no one is interested to answer. Anyway, thank you, Venkatesh. Based on steric effect, maybe less also. Okay. Well, nice. Well, your answer is, I would say, correct, but not greater than 7. I mean, it shows primary kinetic isotope effect actually. So meaning that kh by kT is greater than 1, some higher value. That only we know. And we'll try to get the answer. It's okay. Let's see. And let's come back to our point. So what we have is that iodination reaction, and so in organic, every time we see some unusual activity, we say that there is steric. Okay. which is partially true. Most of the time we see that steric is the main reason. If not electronic, it will be the steric. But let me discuss something else. If you see the current research, like my friends and all of the professors which are doing, it shows that sometimes steric is not the main factor. Okay, sometimes it shows that it can be the most of the time also that some other interactions are doing the um, is the reason for different selectivity or reactivity. It not necessarily every time is steady. Okay, that's a good point. Every time we try to answer in that because it's the easiest way. And sometimes this interaction, so which we call like non-covalent interactions, those are also like very important in reactions, which are not part of this discussion anyway. So let's see what is the mechanism is written and can we follow it or not. So this is the typical mechanism is given. Now see the difference here compared to the earlier case here. So here I have a phenol which is just OH group substituted benzene. I have a basic medium with NaOH. So OH minus is there which abstract the hydrogen, thus becomes H2O and the phenolate anion, right? Now this phenol itself is very electron rich. So what we expect is a high aromatic electron. The rate of aromatic electrophilic substitution is very high, right? Because it's so much dense with electron density. So the fact that it is so much electron dense because of this anion formation, the attack at this electrophile, there is iodine here, I plus I can also say like simultaneously happening, this becomes super fast compared to the like nitration, where we see that the nitration reaction, the benzene was not that much electron rich, that the step was very fast. What happens here, the O minus increases the electron density, I mean in the benzene ring, it is so electron dense that this first step becomes is no more the redetermining step. So here this occurs very fast. Fast, actually faster compared to what? Compared to the second step. Compared to the second step, where there is a cleavage of CH and CD bond. So in that case, this CH bond breaking becomes the rate determining step. So CH bond becomes the this bond breakage. Now if you have a two substrate like one phenol with a ortho substituted hydrogen with deuterium. So you will see, so the rate will be slow, not slow. The kh is faster, kd is slower. That's what I'm saying, that kd will be slow. So this shows that though the two reactions are aromatic electrophilic substitution, it may change. So we see here is a kh by kd of 4.1. So let's say you do the experiment, you will get a value 4.1, which in turn you will conclude that okay, this reaction follow a step in which the carbon hydrogen bond breaking is the rate determining step, not the other step. If you see a kh by kd value in experiment which is very close to 1, then you will say okay, this reaction doesn't involve ch or cd bond in the rate determining step which was shown in the nitration. So though the reaction mechanism is very similar, depending upon the substrate and the electronics and the other steric may be also, the kh by kd value change. So this is the conclusion of this point. Now we'll go to some another reaction here. So this time we are not only dealing with kinetic isotope effect, but also we will try to see Hammett. Okay. So you can do one thing. You can draw the reaction in your notebook. This is very simple. No, not that simple. There are too many structures are here. Anyway, so here we will deal with first of a question, because we are dealing with kinetic isotope effect. What is the kh by kd value, which is in the inside? You can see the green color it is shown. Kh by kd equal to what? That is one question. Whether you expect any kinetic isotope effect or not, which is very easy. Actually, the mechanism is given. At the same time, we will discuss what will be the rho value for, let's say I put a name as a substrate 1 and substituent 2 here. What will be the rho of y value? What will be the rho z value? At least plus minus the number slope. What will be the plus, whether it will be minus, and this 4 point you just mention, and I will give you some time. So think about it. This time I expect please answer. I mean at least few answer. One, two. Everyone. Jagabandhu, if you have any problem, let me know. Ankita, Pallavi, and Christina. That's all I can see. Any more? Yeah. Venkatesh. So you have four fill in the blanks here. Okay, I see some chat. Kh by kt value is greater than 1. Of course, very good. Which we expect because it is the in the redetermining state according to the mechanism is showing that CH bond breakage is there. Hello Nandu, try to join at least 7:5. I generally start at 7:5. So I have shown one reaction. The task is to fill in the blanks. What will be the Hammett value here? To 3 Hammett value I expect. Maybe some plus minus is okay. Anything is okay. And our today's discussion topic is the kinetic isotope effect. What value you expect Kh by Kt? Whether do you expect primary kinetic isotope effect or not? Rho value, guys. What is the rho value? Ankita, very good. Kh by Kd 1 to 7. Nice. And everyone is saying Venkatesh greater than 1. Perfect. Rho value for x is negative, whereas rho value for y is positive. And what about z? If you see the z value, let me show the slide. So the substituent containing the z containing substituent, this ring is having electron density. I mean in the reaction it is getting electrons. Okay, right. So if we have electron withdrawing substituent, we'll have a high rate. So let me come to the answer actually. So first is very easy, like kinetic isotope effect. Of course we will see the kinetic isotope effect here because the rate determining step here involves this. It's a E2 elimination, simple E2 elimination. Okay, so hydrogen will have a higher rate compared if you substitute with the deuterium, it will have a lower rate. So Kh by Kt greater than 1, it should be around 4 to 7 something. And what about the rho value? So if we remember in the last two tutorial session, we have discussed to how to get this value very easily, like how to get it. So let me show it again. It's very easy. So generally we will draw something like this, and sigma with NO2 group, electron withdrawing group here, and electron releasing group will be here. Let's say NH2. So in the Z, for example, this sulfoxide. So here, if it is electron withdrawing group, we expect this, of course, K rate log of K something will be here. So we'll have a point here, and NH2 we expect to be here. Rate will be less. So if we can draw a line, so slope is positive. Slope is positive. So for the Z we expect positive value. Similar goes for y. Y is having some sort of development of negative charge here. So if y is electron withdrawing, again it will have a higher rate. Whereas x, the charge is going from it to the reactant, going from itself to the reactant. So NH2 or other thing will have a rho value. So what will happen? So it will have a something like this. Sorry, this line is something like this. So we expect a rho value of negative value here. So negative value. So x we expect negative value, y we expect a positive value, z also we expect a positive value, right? Kh by kt greater than 1. So now let's see the answer. I think I have added it here. Exactly, that matches our approximation. Well, kh by kt is 7.1, which is, I thought that it would be less, but it is 7.1. Okay. So again, rho x, which is minus 4 point rho, it has a very high effect, minus 4 compared to the, see, plus values are not that much effective because there is not fully grown negative charge. So now let me discuss the magnitude of this value. Okay. So why it is minus 4 kind of value, why it is plus 2.6, why it is plus 1.1. We got the sign accurately, right? We got the kh by kh, we expected a little low, but it's very high, 7.1. So this involves at the redetermining step, and this is a linear symmetric stretch we can think of because it is very high value. So this rho value of minus 4, it's relatively high compared to the other value. We can say that it has a very high impact of this substituent. Like if it is NH2, it will be faster. If it is like OMe, it will be faster. Remember, we are talking about meta and para, not ortho, because Hammett applies only for meta and para. So these has a higher sensitivity. This phenoxide, I would say, substituted phenoxide. Compared to the here, because see, this is an E2 elimination, and if it was an E1, then there should be some carbocation type character, and since there is a no full grown negative charge at this position, so it will just come and it will go at the simultaneously. So the substituent effect on Y, though it is close to this negative charge formation, is close to this substituent benzene ring, so it has a relatively high value, 2.6. Now compared to, if you come here, it is more or less like 1.1 compared to it is 2.6 at least, because the negative charge is mostly delocalized within this part. This SO3 minus group, SO3 minus group. This negative charge is not conjugated with this benzene ring. I can, if I draw it, minus charge will come here and it cannot go there. It will be mostly will be rotate. I mean, the cloud will be mostly on the SO3 group, SO3 minus group, not on the benzene ring. So you see the number is very less compared to the other two number, 1.1. So these are the things we should be following all the time. What are the number? What are the sign actually, plus or minus? Whether we expect a positive or negative, and then what are the magnitude? In the magnitude, we may be wrong because it depends, but at least we should have some idea or some explainable part where we can say, okay, this should be higher in this range, this should be in the lower range, which I taught in the earlier class. And if you follow the Clayton book, it is very well written. So this was the question, and it involves a lot of things. Now we'll come to a little complicated thing, which is, I will try to explain. Let's see what is there. Let me give some time actually. Up to this, any question? Anyone have any question? How many participants are there? 7. Okay.
Sir, excuse me, sir.
Yes, yes.
In the slide 8, please explain once again about the Z value, sir. Rho Z.
Row exact value for all x, y, z.
Yes, sir. Z and X, sir. X and Z.
See, x, this O minus is directly conjugated with the benzene ring, right? So substituent will have more impact because this negative charge was conjugated with the ring. So that's why it has a high magnitude is large, 4, because this is directly involved with the benzene ring. Whereas forget about the sign number in the Z substituent, here you see the negative charge which is forming here is not directly involved with the benzene ring. I mean resonance, in terms of resonance. If you see that minus charge, you cannot delocalize to the benzene ring. The pi electron can come here and then it is conjugated with the sulfur. So there is something called branching. I don't remember the exact term, but it shows that, see, O minus is, it will be mostly covered by the SO3 minus group, not with the substituent. So substituent effect on the Z is very less. So that's why the magnitude is little low number here. Did you get it?
Sir, yes, sir. Sir,
Okay.
suppose if X is the electron withdrawing group, then
Hmm.
rho value will decrease, is it?
So let's say X is NO2 group, para position NO2 group. Okay. So what will happen? This O donation to the hydrogen here, it will be lower, right? Because the O minus will be conjugated with the nitro group.
Yes, sir, yes, sir.
So it will lower the rate. It will lower the rate actually. If you have NH2 group, it will push the electron more. So it will have a higher rate.
Thank you, sir. Thank you, sir.
Okay. So now let's go ahead and see what else we have. Now things will be little. Let me try anyway. Now, in the earlier cases, primary kinetic isotope effect. So we are assuming that in the redetermining step, the CH bond is getting killed or CD bond, whatever. Now there may be situation which is CH bond or CD bond is not breaking in the redetermining step. So in that situation, what value of kH by kD we expect? Whether there should be any number, what should be the number? Okay. Now there is a one example here you follow. In the earlier example, like first picture, we showed a single red dotted line here, which is not actually, true. Which is not actually true. It is some assumption. Okay, it's very close. The point was very close. Now we'll go into a little deeper. So again, the same potential energies. Electron here, surface is there, and you see the lower is the CD bond. Okay, this correspond to CD bond, and the higher energy level, vibrational energy level, correspond to the 0 point energy. Here it correspond to the CH. I cannot write here anyway. So this difference in the ground state. So Gs, the what I am saying. So this will the difference between the CD and CH, 0 point energy. So delta 0 point energy ground state difference. So difference of 0 point energy in the ground state. So see there is a high magnitude here. So the magnitude of this difference is a little high. Now you come to the transition state. Here, what you see in the picture, the difference CD, of course, it will be lower and CH is there. So the difference between 0 point energy, delta 0 point energy in the transition state. So actually the main point is that this kH by kD value, if it is not primary kinetic isotope effect, mostly it will depend on the transition state structure, like how it is approaching and how the CH bond is sleeping. So there can be multiple orientation and different angles, geometry, bond distance. These will alter the transition state structure, and based on that, this in the transition state, the difference between 0 point energy will be different. So it will vary from molecule to molecule, reaction to reaction. Of course, the ground state also. But remember, we are talking about the magnitude of these two things. So magnitude of 0 point energy difference in ground state will compare with magnitude of 0 point energy in the transition state. And then this difference of these two situation is the shown in the equation. Delta 0 point energy ground state minus delta 0 point energy transition state, which is delta delta G star. So this information is necessary to understand the next slides. Okay. Please remember that we have a delta Zp in the ground state, we have a delta Zp in the transition state. Generally, the difference is more in the ground state compared to the transition state. Okay. Uh, that's why we see that a primary kinetic isotope effect. For example, if you see here from CH to the CH, the activation energy is less. From CD to CD, the activation energy is high because in the ground state CD is lower in energy. CD is this difference being high, the CD is much lower in energy compared to here. So the CD has a higher activation energy, rate is low. So please remember this picture, it will be handy in the next slides. Well, this I took from the internet, you can get it also. There are a lot of informations are written in this slide. So uh, let me say this in this way. So let's say this kH by kD value, we've seen that it showed like 4, 7, 3, 2, very high value. More than 2. So the boundary, let's say 2 to 7 is we will I say that okay, there is a prominent kinetic isotope effect. So there are some situations in which the CH bond is not break in the redetermining state. But then also we find there are some value of kh by kd. If you show in the box at the right side, there are value like 1.1 to 1.2, 0.8 to 0.9. These situation where the CH bond is not break in the redetermining state. So and the value is low. This we will say like secondary kinetic isotope effect. Okay, secondary kinetic isotope effect. Now, in this figure, there are a lot of things, but I will say some point like you see in the rule of thumb, imagine a reaction you are going from sp3 to sp2. I will show reaction, don't worry. So, imagine you have a reaction where you are moving from sp3, I mean, ground state, you have a sp3 molecule, I mean, reaction center. You have a carbon hydrogen bond there, and whatever the reaction, ch bond is not involved in the redetermining state. Ch bond is not breaking. 3 point, remember, you have a molecule in the ground state, it undergoing a reaction, it has a ch bond which is not involved in the redetermining state, it is not breaking. So these are the point. Now, so this potential in the surface and all we are talking about. So there is CH bond. We are interested CH bond. Now, if you see the vibration, so there are so many vibration. Which vibration I am talking about? Whether it is in plane bend, out of plane, symmetric stretching, asymmetric stretching. What are the important vibration? So these are the important point. Now, mostly we didn't talk about what kind of vibrations are important. We didn't go that detail, but some informations are necessary to understand the secondary kinetic isotope effect. So, in plane bending in sp3, you see here, in plane bending, you see this bond and then this bond. My cursor you follow. So, let's say hydrogen is, I mean, motion is like this. So, this in plane motion, and in the transition state, it has a character like sp2 character. So you see that now since it is sp3, this all other substituent like this OH bond and then a coming bond and then single bond, all it will have a more crowding, more crowding. So this vibration and it is coming, so all nearly same 1350 1350. Now in the out of plane vibration, CH vibration is, see that there's a drastic difference here, 1350 to 800 centimeter inverse. So this out of plane bend is the actual factor in secondary kinetic isotope effect. So I will discuss this point actually. So out of plane bend, how it affects the value. Okay, there are a lot of things. Let me follow this line. This two line actually important. Imagine you are going from sp3 to sp2. The out of plane bend weakens. What I'm saying, out of plane bend weakens as the reaction approaches to the transition state, making 0 point transition state, 0 point energy transition state less than 0 point ground state, which is the situation. This transition state lower value, lower difference, ground state higher difference. So this is the situation. It will give you a normal kinetic isotope effect. So if you have this situation which is shown here, it will give you a normal kinetic isotope effect, meaning that you will have a 1.1 to 1.2. Why? If you ask why the number is less, because the CH bond is not breaking in the redetermining state. Again, I am saying if we have a situation like this where the 0 point energy ground state is large, TS is low, we will expect a value normal kinetic isotope effect. This situation can get inverse, meaning that the value can be lower than 0, lower than 1 also, lower than 1 also. When it is moving from sp2 to sp3, the situation is just the opposite. The out of plane bend strengthens as the reaction approaches the transition state. What is the corresponding consequence? The delta Gp Ts greater than the delta Gp ground state. If you come to here in this picture, the difference is less here compared to the difference here. So in the transition state, we will have a slightly higher difference compared to the here. Let's say here there was a difference of 4. Let's say there will be difference of 4 point something, 4 point x, 4.23. So these two differences get reversed. So that's it shown. So all this happens, all this happens due to this bending mode. So bond strength as the reaction approaches the transition state. out of plane bond strengthens. So it increases, bond strengthens, reaction approaches. The result is that the TS 0 point energy is greater than ground state 0 point energy, and this gives inverse kinetic isotope effect. Remember, these two are secondary kinetic isotope effect. CH bond is not involved in the redetermining state. Again, so it will have expected isotope value of 0.8 to 0.9. Okay, with all this information, let me show you some examples so it will be clear. Um, so for the SN2 reaction, this CH3Cl or CD3Cl, so there is no cleavage of hydrogen, carbon hydrogen or carbon deuterium bond. This is a simple substitution. And SN2 reaction, we are having a kH by kT value, so, I mean close to 197.97, which is which can be round off to 1 sometimes, like kH by kT is 0.97. So because it's a secondary kinetic isotope effect, because there is no breakage of CH bond here, and the reason what is written I found is that the CD bond is shorter relative to the CH bond, which is makes sense. CD bond is shorter relative to the CH bond, allowing the nucleophile a less hindered approach to the electrophile. So CD bond is short, so it gives a less hindered approach. This reason is not so, I don't find so appealing, like very good, but I got this, and you can take this and I can find also other things. Whereas in the SN1 reaction, you see here kH by kD value of 1.13. So this value is relatively higher from the first one. So here this OTS is giving clip. So it's a carbocation formation. So carbocation formation. Now remember, so initially it is sp3. So it is sp3 carbon center. I am talking about this hydrogen replacement. Remember CH. So remember, if you replace this hydrogen with deuterium, what is the effect? So this and this both will form carbocation, and carbocation means it is a sp2 hybridized. So from sp3 to sp2, which correspond to this situation, sp3 to sp2, and we expect a value between 1.1 to 1.2, and we see it's a more or less same range. So kH by kT of 1.13. I hope it makes sense. Now let's see what they have written. The normal kinetic isotope effect found for this reaction implies that it is not going by an SN2 mechanism. So it will have the inverse kinetic isotope effect. The KIE here mainly arises from changes in hybridization. So it is very clear that there was no change of hybridization. There. Of course, in the transition state, it's TDP kind of structure. But here there is a two steps, and there is a sp3 to sp2 formation. There is a it's very strong. We have evidence like sp2 to sp2. So hybridization change is prominent, very prominent. So that's why we have a value of this. Whereas in the SN2 reaction, the change in hybridization was like sp3 to kind of TBP structure to again sp3. So in SN1 reaction, there is a clear cut, formation from sp3 to sp2, and there is a high, this kH by kT value is 1.13. So mainly arises from change in the hybridization. Now I have a few more questions which are from Carey and Sandberg. Examples are already given. Let's see. Okay, where is it? And these are very easy, and we will just take the answer and we will stop. Okay. I will ask directly some of you. Just answer, okay, please. These are very easy. We just have to say what kind of isotope effect, primary, secondary, and if it is secondary, if it is normal or inverse. These are the things you have to say. So I will ask Pallavi, can you say the first reaction? It is primary kinetic isotope effect or secondary? And if it is secondary, it is normal or inverse? Just write it in chat box, or you can just unmute yourself and say it. Hi, are you there? No problem. So who else is okay? Primary isotope effect. Thank you. Very good. And primary isotope effect. So there is no problem. And why do you think it's primary isotope effect? Okay. So because it is the steps involve the breakage of CH bond. So this hydrogen is involved attached to the Br radical. So H radical will combine with Br radical to form HBr. So CH bond is involved. Okay. So that's why it's a primary kinetic isotope effect. And the value I have not written. So it's around 4. So if I see in the book, it is 4.6. Okay. I'm not showing here. Now, thank you, Pallavi. And who is anyone else? I can see. Uh, Jagabandhu. Yes, Jagabandhu. What do you expect the second value? Sorry, second reaction. Question is primary kinetic isotope effect or secondary? If it is secondary, inverse or normal? Three question. Magnitude we are not interested right now. Chat box. Second reaction, Jagabandhu. I didn't show the red color hydrogen actually. In the product, it is there. You want to answer, Jagabandhu, or we should go ahead? Okay, no problem. So see, there is no breakage of this CH bond here. It is actually there. So we don't expect a primary kinetic isotope effect. We expect secondary kinetic isotope effect, and it is going from sp2 to sp3. It is going from sp2 to sp3. So we expect an inverse kinetic isotope effect. Now, if I check the result, what we have. Uh, Yes, from CHO to HCN. Yes, so it have 0.73. So second, let me write it actually. KIE equal to 0.73. This chart won't be there anyway, no problem. 0.73. So the second reaction has a KIE value of 0.73. It's a secondary kinetic isotope effect, and it is inverse. Now, who else? The third question, I can see Venkatesh. I will come to you last. Don't worry. Christina C. Christina just answered the third question, whether primary or secondary, and if it is secondary, normal or inverse. It's very easy actually. Any response, Christina? Just primary or secondary? Just wait. Secondary isotope effect. Why do you think it is secondary isotope effect? You can unmute and also say it's not a big deal. Okay, so are you typing or I don't know. So anyway, so but this is a primary kinetic isotope effect. So this is an enolate formation. Actually these two hydrogens are equivalent. I have shown only here one. See, this OH minus will abstract this hydrogen. And then the CH bond will break and it will form an ion which is like conjugated. That's why it is shown here. So in the this step, this is one step only. In the this step has the CH bond breaking, so it will be a primary kinetic isotope effect. So this CH bond breaking is there, so it's a primary kinetic isotope effect. So I will write primary, and so what is the magnitude? It should be 4 to 6 kind of. It has 6.1, so it has 6.1. So that was the third reaction. Nice. Thank you, Christina, for answering. So we'll go another set of questions which are similar to this. Hmm. So I can let me check you now. Who is there? I hope you are not bored that much. Ankita Panda, please answer in the chat box. What do you expect the first reaction in this slide? Primary, secondary, or normal or inverse secondary? So we'll end with that 8. Okay, secondary. Good. Secondary, and because this CH bond is not breaking, so it has not that much effect, and KH by KT value should be around 1. And if I check the values, it is like what is written? Yeah, 1.30. It's a secondary, and it's a normal 1.30 because it is the hybridization changes. See, sp3 to, I mean sp3, that is, it's a SN2 mechanism, like, so it should be like that. And now the second reaction, who else is left? Yes, Venkatesh, go ahead. Venkatesh, can you see the slide?
Yes, sir. Yes, sir.
Second reaction, just to say primary or secondary.
Elimination reaction. Sir, it's a primary kinetic isotopic, sir.
Okay.
Elimination reaction.
Elimination reaction. But it's a little bit unknown reaction, I think. Is it so, Venkatesh?
Yes, sir. Yes, sir.
Do you know the mechanism?
No, sir. No,
Okay,
I don't know,
that's.
sir.
I mean, it's okay. You can just say it. It's okay, no problem. Uh, Actually, this reactions is not taught, but I just showed that it was an example that I took. Anyway, no problem. I will show it. The mechanism is very easy. Just a second. So I need to draw it actually. I hope you have time, so I will just show it. Don't worry. So let me draw it as it is. So you will see a lot of questions actually in the books. You will find other question. You can solve those things. This is not correct. Sorry. So it belongs to pericyclic reaction. Okay, and of course it's an elimination reaction. That's correct. You noticed. So there are hydrogens. So basically CH2 here and CH2 is there. So how it is happening? It's a concerted mechanism. So you see this bond. Let me change the color. So this bond will break and come here. It's a pericyclic reaction, and this will come here, and this bond will break. Now let me complete it here. Oh my god, I took too much space. So what will happen? Sorry, this will be. So what will happen? You start with the same thing, and you have a this structure. So see, this double bond has appeared here. So it has appeared here, and it was already benzenoid structure, and this bond has moved here. So it will come appear here, and this was already there. So this we got, and this separated like ethylene CH, right? Now, since this doesn't involve any breakage of CH bond at the this mechanism or any redetermining state, so we don't expect primary kinetic isotope effect. So we don't expect any primary kinetic isotope effect. Now it is secondary kinetic isotope effect. So it is secondary kinetic isotope effect. So 2 dB, I will write. Okay, secondary kinetic isotope effect, and the value magnitude. So see, it was sp3. Here it is sp3. sp3. In the product, we see it is going to sp2. So it is not inverse. So it's normal secondary kinetic isotope effect. It is normal secondary. I write 2 dB. Okay, don't worry. So this is the situation, and did you get it, Venkatesh?
Yes, sir.
Okay, okay, nice.
Yes,
Yes,
sir.
sir.
Thank you,
Thank you,
sir.
sir.
Thank you.
Okay. Now I don't remember the magnitude. Let me check it and put it in the chat box. You can see it. It has KIE value of what 1.37, which is okay. There you go. And the last reaction, I think no one is here. I mean, extra. Yeah, that's all I see. Some people. Jagabandhu Krishna Gita Pandavi Venkatesham. So this will answer. I will answer. So H minus will abstract this hydrogen, and it's an E2 elimination. So this will come. So it will have a primary kinetic isotope effect. Very easy, nice and cool. So it has a value of 4.0 again. So that's all I have for you today, and thank you very much for participating, and hope to see you in the next class. Thank you, everyone. Thank you.
Thank you, sir. Thank you, sir.